I want, and I'm going to do this on the board. I want to show you some graphs. As you know, we care very much about graphs. Graphs is the way of communicating in engineering. It's not words. We don't talk. Social people talk. We don't. But we make drawings, and this is the way we explain to each other. And across the world, these drawings make sense. So, heat exchanger schematics. So, I'm going to make this simple heat exchanger here, not because all heat exchangers are simple, but because this helps me explain the concepts without getting distracted with things. I don't want to get distracted now. So in this heat exchanger, first of all, what type of a heat exchanger would this be? A parallel flow, and would be a concentric heat exchanger too, right? Very inefficient, by the way, right? This is a tube inside the other tube, right? But the most important thing is a parallel flow. Now, let's say the flows start mixing here and finish mixing. The temperature exchange is between these 2 points. I'm going to call this point 1 and this point 2. If you like to flip 2 and 1, it's all the same. Doesn't matter, right? So when we talk about 1 and 2, it's just one with the 2 points in the heat exchanger. Doesn't mean inlet and outlet, doesn't mean start and finish, doesn't mean hot and cold. But once you commit to 1, everything has to be consistent with that 1. I'm going to make this other graph. So this is going to be temperature. This is x. This x is the distance into a tube. I'm talking here about internal flows, right? This is the same x that Ying taught you about when she discussed internal flows. In heat exchangers, it's like a tongue twister. The main thing is not to get confused in the naming of things, because if you get confused in the naming of things, everything goes wrong. Let's say, in this case, doesn't matter which is hot and what is cold. I'm going to make the temperature profile for hot fluid, meaning temperature of the fluid versus length into the heat exchanger. What does this curve look like? Is it flat, up, or down? Down. Okay, thank you. Now, tell me, if the hot fluid goes up, that means the hot fluid is getting hotter, right? There is your Nobel Prize, right there, violating the second law of thermodynamics, right? The hot fluid gives heat away, it doesn't get heat. And now every year, and I'm pretty sure it's going to happen, somebody does this one. The hot fluid gets hotter, right? It never fails. And I give you warning, right? So the hot fluid is going to go down. And I'm going to start giving names to things. So this is going to be T, hot fluid, inlet. The I means inlet. Now, part of the tongue twister, and this is something I have to figure out, the book is not consistent, so I'll need to do it myself. Sometimes the book uses I for inside and O for outside. But in heat exchangers, it's inlet and outlet. Although when you have an internal flow, sometimes it's I and O again. So it can be confusing. So whatever the notation is, you have to know what you're doing about. Don't just memorize TIO or whatever, THI or THO, because it can bring confusion. So now this is T of hot at the outlet. Right? Are we all on the same page so far? All right. Let's do the cold. Up, down, or flat? I like that. All right. So this is going to be T cold at the inlet and T cold at the outlet. So this one here, this would be delta T 1. You're going to see how we use this later. Here is delta T2. This one here is delta T of the hot fluid. Delta T of the cold fluid. Something I'm going to ask you to do in the exam. Mark the direction of the flow. I want to discuss this curvature. You see that this thing is going flatter? Here, how intense do you think is the heat exchange on 1? Very intense or relatively weak heat exchange? Intense because it's a big difference in temperature, right? Because we have a big difference in temperature, then the temperature change is relatively fast. So the slope is steep. Now here, the temperatures are quite close, right? So we have a shallow heat, we have a weak heat exchange, and we have shallow curves. Now just think of this. This little length of heat exchanger is buying me a whole lot of heat exchange, right? This length of heat exchange is buying me pretty little heat exchange, right? Now, the cost of a heat exchanger is proportional to the size of the heat exchanger. So my money is so much more worth here than here, right? So when the temperatures get close, the heat exchanger becomes inefficient. And this is called the approach temperature. The approach temperature is the minimum temperature difference between hot and cold fluid, right? So this was for parallel flow here. So let's do the same story for the counterflow. So I'm going to make this schematic. And one of the reasons it's so important to do this is because very complex heat exchangers, we treat them as if they are counterflow. Just say, let's assume it's counterflow, and let's use a correction factor. And somebody already thought the correction factor is for you. In the counterflow, one of the flows goes this way. How does the other flow? Left to right or right to left? Left. Right to left, right? So again, I'm going to call this 1. I'm going to call this 2, just because I liked it, but once I said 1 and 2, I'm committed. And I'm going to make my graph. So this is x. This is temperature. I typically ask you in the exams, I'm going to do it here, to mark 1 and 2, or inlet and outlet in the diagram. You have to know what you're doing. Okay, so let's say, much like before, we have this hot fluid. So here we're going to have T heat, hot inlet, T hot outlet. All right, what is the curve for cold flow? What does it go down? Does it go up? Is it flat? Goes down? All right. Okay, well, I didn't mean it to be tricky, but it's kind of tricky because, right, if I go from left to right, it goes down. Right, right to left is up, right? And that's the way it goes. So T cold inlet, and now the T cold, oh, thank you, so much better. Right, and so now we have delta T2. But I draw your attention to this. Delta T2 is a delta T on the side 2, but look, this is hot outlet minus cold inlet. Well, here was hot outlet minus cold outlet. You see? So here you just gotta know what you're doing. It's like delta T2 is delta T2. It's unrelated whether it was inlet or outlet or whatever it was. And here we have delta T1. And the slopes is the same story as before. The slopes here, because this difference is smaller, the slope is shallower, right? Now, this type of heat exchanger is a lot more efficient, because in this other one, you go from a huge difference to something that is not so big. And you never, the hot, this is a funny thing. The hot fluid is always hotter than the cold fluid, right? But a funny thing about this type of heat exchangers is that you have something that is called a cross temperature. You have a cross temperature. So you have something that is quite amazing in counterflow heat exchangers, that the hot fluid can be colder than the cold fluid, right? Of course, it's not at a given point, right? We're comparing different parts of the heat exchanger. For this reason, counterflow heat exchangers are so much more efficient. You want those when you can, right? And cross, right? And of course, this one here, that if this one is small, this is also delta T approach, the approach temperature. So these are definitions. I think this is the most difficult part of heat exchangers. Here are the definitions of approach temperature. You don't need to memorize any of these numbers, but I wanted to include them so you would have them in your notes. About typical values that people in industry report as reasonable approach temperatures. That those values there are kind of a rule of thumb, ballpark about, okay, how big our heat exchanger should be. If I want a smaller approach temperature, the heat exchanger is going to be much bigger for no good reason.